I've happened across some YouTube videos, actually quite a few in recent years, where various people, mostly from industrial controls training institutions, or more often from manufacturers of industrial controls, especially sensors of various types, or distributors of same, are trying to explain some of the more mystifying characteristics of wiring up the sensors, especially in regards to connecting them to PLCs and so on. I found that in the majority of these, the people don't seem to have a very firm understanding themselves of what's going on, and they're relating more of a rule of thumb, or they might know what's going on, but they're so bad at presenting it that a neophyte might come away more confused than they were going in. I worked in industrial controls for, 45 years, something like that, and been working with various types of sensors that whole time, and I thought, I'll just try throwing together something and maybe it'll be of use. This isn't something I put a lot of time outlining and practicing, so it's going to be a little bit shooting from the hip, but still I'm hoping I can be as consistent and clear as I can make it. So this is primarily dealing with various types of sensors that might be wired into either a relay logic circuit or into a programmable logic controller, in other words PLC, input module, or into a distributed control system, otherwise known as a DCS. And to that end, I'm going to be talking about three-wire sensors in particular, those that are powered from a circuit which is also electrically common with the input device. And I'm just going to simplify it and say that most of the time it's a PLC. So again, these are most commonly done with three wires, so I've depicted three wires. A lot of times the sensors are cylindrical in nature, so they're something you could put through a hole in a piece of equipment and put a nut on the other side. It might sense proximity of metal using magnetic sensing techniques. It might use a capacitive system where it's dealing with the proximity of various objects, not just metallic ones. You may have ones that use an infrared light beam that's either broken by something coming in front of the light, or maybe it sends out a beam of light, it bounces off of something and comes back to the sensor. A lot of different things. It could even be a sensor that detects temperature or vibration or something like that. Could be a lot of things, but still they could be in this basic form factor and they could still have three leads. Sometimes you'll see sensors that are in a so-called hockey puck format, so they're physically a fairly low and round case, and they may just condition a signal. For example, you may have some wires, it could be two or more, going off to the actual sensor, and then circuitry inside the hockey puck conditions that and then provides the usual three wires for power and signal. So you may see that configuration, or you may see them in other configurations. Here I've just shown a box. It could be a little control panel, or it could be something that's neither a hockey puck nor a cylindrical device, and it still is a three-wire sensor. So with that in mind, let's get into some of the details. So first I want to talk about the types of switching technology that are used in sensors. The first one is the contact. You don't see this a lot in the cylindrical type of device. You may see it in the hockey puck type. It's quite common in other types. The main reason you don't see this in smaller sensors is because to be a contact requires a relay Relays are large and take up space. Even small relays take up more space than solid state techniques. So you still have contacts, you have to be aware of them. These are just shown like this in normal industrial control symbology, although sometimes you'll see them depicted like this. This is technically the symbol for a relay contact. This is technically the symbol for a switch contact, but you'll often see people showing a relay contact as if it was a switch. They're electrically the same thing. Now you'll have transistors, which are used in low voltage DC applications. And this is probably what you'll see the most, especially if you're wiring into a PLC. And this is broken down into two types, the PNP and the NPN. This is just terminology for how the transistor is constructed internally. You can think of it as positive, negative, positive, or negative, positive, negative. That's not really quite correct, but you can still use it as kind of a memory refresher. A transistor is a three-terminal device, but for our purposes we're only concerned about the part of this transistor that's handling current to a load. Here's the PNP transistor, here's the normal schematic symbol for it. I'm omitting the base signal which comes in here. I didn't even show it, but maybe I should pencil it in there. So I've shown the base wire, but I'm just not showing what's connected to it, and we don't care. With a PNP, the side with the arrow, this is called the emitter, and the arrow is always the emitter on a transistor. So on the PNP, the emitter with the arrow is always connected to the highest voltage potential in your circuit. So let's say that your circuit is a 24 volt DC supply, which is very common. It's the most common voltage used in industrial controls for when it's DC. So this would be the positive side of your DC power supply. We can call it V+. And then the other side of the transistor, this is the collector. It's the side without the arrow. Goes to the load. Now the load is going to be whatever is accepting the signal from the sensor. So let's say you have a sensor that's detecting the proximity of something. When that proximity is detected, the transistor will turn on and current will flow from the V+ into the emitter, out the collector, and then off to the load. In order for it to be a circuit, it has to continue from the load and go back to the other side of the power supply, which we might call ground, we might call it common, we might call it V-, various things on the other side of the load. But for the moment, let's not worry about that. It's just a PNP is always connected with its emitter or the arrow side to the positive voltage supply. Now for the NPN transistor, it's just sort of upside down. In this case, the collector is connected to the load, and the emitter, the side with the arrow, is connected to the circuit ground or the circuit common or the, I accidentally wrote V+ here, that should have been V-. Let me fix that. There we go. Now the current in conventional current flow, we're not atomic physicists here. We're not worried about the fine details of the underlying physics. We're just trying to deal with the conventional way of looking at things. In the conventional current flow, current flows from positive to negative or positive to common. As the current flows from positive to negative or positive to common, you normally don't have negative voltages, actual negative voltages, in industrial control situations like this. When I say negative, that's just referring to the minus side of the DC power supply. So it'll have a minus sign, but it isn't negative, it's just minus. So in that conventional current flow, current goes in the direction of the arrow. So you can look at the symbol and see which direction the current has to go through the transistor. Remembering that the emitter, or the side with the arrow, always goes to the power supply. So on the PNP, if you want to think about it this way, the arrow or the emitter goes to the positive side of the power supply. And the NPN, the emitter or arrow side, goes to the minus side of the power supply, often called circuit ground or circuit common or V minus, even, various different ways of depicting it. But that is the simple way to visualize what's happening. These just behave like switches. To the stuff out here, it's no different than a switch or relay contact closing, except in the case of contacts, current can go in either direction through the switch. With the transistors, the current must go in the direction of the arrow. Now there's one other choice with sensors like these, and that is if you're dealing with a higher voltage, such as 120 volts, and it's AC, so you're operating things that are connected to the AC power line. In that case, you cannot use the transistors. Number one, they're not rated for that high of a voltage. Number two, they're DC only, so they cannot be used with AC. So the most common switching device in sensors that are connected to, say, 120 volts AC is the TRIAC, sometimes also called a solid-state relay. It deals with the current going this way and the current going this way that alternates 60 times a second, or 50 times a second if you're not in North America or a few other places. But again, to everything outside, it seems as if it's just a switch. Now, because there's no positive or minus on this, it doesn't matter which side you put the load on or which side is going to the power source. It could be either side. Although on particular pieces of equipment, the manufacturer may stipulate that one side goes to the line, meaning the AC line, and the other side goes to the load. And if they do stipulate that, then you have to follow that. So let's look at the transistors by themselves, excluding all the other options. So just to recap here, the transistors, when they're used inside sensors, it's always for a DC circuit, and in industrial controls, it's almost always a 24-volt power supply that's 24-volt DC, although other voltages can be used, of course, but 24 volts is the most common. You've got the transistor that's inside the sensor, and you have a load. That could be a number of different things. You've got V plus and ground, which is also V minus. And let's just look at this. Here we have the V plus, that's your positive voltage. It goes through the PNP in the direction of the arrow, entering on the emitter, and then exiting the sensor from the collector of the transistor, and then to the load, through the load, and then returning to the power supply via the ground connection, or common, or V minus. So in this sense, if you're just looking at the sensor part of the circuit and its relationship to the load, the sensor is sourcing current into the load. In other words, the transistor is the source of current that the load is using. So this is considered a sourcing sensor. The load, by contrast, if you look at it from the perspective of the load is sinking current from something else, but we're usually doing this in reference to the sensor, so this would be a sourcing sensor arrangement. Now, if we have a NPN transistor inside our sensor, The V plus of the power supply is up here. It goes directly to the load, through the load, comes out, goes into the NPN transistor in the sensor via its collector, flows through it in the direction of the arrow, current exits the transistor via the emitter, and it returns to power supply ground or common or V minus. In this sense, looking at the sensor, it is sinking current from the load and the power supply by extension. But in relationship to the load, it's sinking current from the load, so it's a sinking sensor. If you always remember this configuration, power supply, transistor, and load, and what the relationship between the sensor and the load is, it's pretty easy to visualize whether it's sinking or sourcing. So a reminder on this, if you've got a PNP arrangement, it's always on the high side of the circuit. So it's closer to V plus, and the load is then closer to the ground or common. Whereas with the NPN, it's the transistor in the sensor that's close to ground and common, and then the load is up here. Let's look at some different scenarios for sinking and sourcing. Let's take this example. We have our positive power supply connection up here. We have a sensor with a PNP transistor in it. We have a load. In this case, the load is the coil of a relay. And then we've got ground, or again, common or V minus over here. So you have to remember there is a PNP transistor in this, and we know that the PNP transistor is always on the positive power supply side of the overall circuit. And that current exits the sensor and then goes to the load, the relay coil in this case, and then back to circuit ground. From the sensor's perspective, it is sourcing current into the load, so it's a sourcing transmitter. If you were looking at it from the perspective of the coil, it's sinking current from the sensor. So again, it's always relative to what your frame of reference is, but most often it's from the frame of reference of the sensor. Now, since it's a DC relay coil, it may have a polarity to it, so you always have to be careful with that too. If the relay coil has a plus and minus marked on it, you always want to make sure that the plus side is the one that's in the direction of the plus of the power supply, and likewise for the minus going to the minus side of the circuit. Let's look at a situation where we've got a NPN sensor. V plus is still up here. This time we've got a lamp. It's a DC lamp, probably 24 volts. And then we have an NPN sensor down here. We remember that the NPN type is always closer to the negative or ground side of the overall circuit, and the load in this case will be up by the positive side of the power supply. The sensor being an NPN type, it sinks current through it to ground, and so this would be considered a sinking sensor. But if you were the lamp might say, hey, I'm sourcing current, but again, the frame of reference is usually the sensor. Now let's look at what happens if we're going into a PLC input. Well, here's one situation, and I've decided to draw this one the way it often appears in industrial control schematics, with a ladder diagram type arrangement. The positive power rail going vertically, and the minus side, or the ground, or the common, is over on the right hand side of the ladder. And then the sensor, remember it's a 3-wire device, I've got a PNP type here. Its positive power supply side is going to the V plus rail. Its minus side is going to the minus side of the circuit. And then the output, which would be the collector of the PNP transistor that's in there, it's taking current and going through the transistor and out the output. In that sense, it is sourcing current from its perspective. Now it goes into the input of a PLC. This would be a DC input module, and then it returns to the ground side of the circuit. From the perspective of the input module, it's a sinking input because current is coming into it in order to get to ground. So again, perspective. We can have the perspective of the sensor. It's a sourcing arrangement. The perspective of the PLC input, it's a sinking arrangement. But if you always envision it this way, it's very easy to tell which one is which. Here's another way of drawing the circuit, this time with an NPN sensor. It's 3 wires. One of them is going to V+, the other one's going to circuit ground, and then the output is here. The transistor is between here and here. And being an NPN type, it's sinking current from its output to its minus side of its power wiring. So it's sinking current, and that's connected up to the input of the PLC input module, which one way or another, current is coming from the V+, which is connecting to the module and going through it and exiting on the way to the sensor and then on its way to ground. So from the PLC's perspective, it's a sourcing input. Same arrangement as this, but flipped to an NPN configuration and drawn using a different style of schematic representation. Now let's take a look at what's inside a typical PLC. And this is again referring to DC input modules. This is very common, just the way I've got it here. This is the input terminal. There will be some sort of a resistor for limiting the current, and then there will be an optocoupler or an opto-isolator, which is an LED and a phototransistor in one assembly. This side of the LED goes to circuit ground or common, and the emitter of the transistor goes to here. Now this could be a PNP transistor. It doesn't really matter to us. All we care about is that when we have current coming in here into the input of the module, it's current limited to a safe and reasonable level. Then it goes through the LED, causing the LED to light up. Light from the LED turns on the phototransistor, and then the rest of the circuit in the input module sees that this is turned on, and it reports that status back to the computer part of the PLC, saying now that this input is now energized. So the current must flow in this direction. Now there are some PLCs which allow for either polarity of DC to be applied. In that case, they either have parallel but opposite facing LEDs. That's one way. Another way is to have a diode bridge in there that always routes the current through the LED in the same direction, regardless of the direction of current coming in or out of the input module. So when you're using transistor sensors in a circuit where you've got relays doing a lot of the work, this is very obvious how it works out. All you need to do is have your power supply, your sensor, and the relay coil, and make sure you have the polarities right, and it's a done deal. The sensor takes power from here and sources it to the load, and then it returns to ground. Maybe you're using the sensor to operate a lamp on a panel, for example. And in this case, you might decide that you want to have the lamp connected to the positive rail, and that would force you to use an NPN type sensor because it's going to be on the low side of the circuit, sinking current through the lamp back to ground. So sometimes these things are no-brainers. Something will force you to have the load either connected to V plus or connected to ground, and that forces you to use the appropriate type of sensor. Other times the sensor may be defined. It's only available in a PNP or only available in an NPN, or some other factor requires you to use one or the other. And then you just have to arrange the rest of the circuit so that the sensor is on the appropriate side of the circuit, either close to V plus or close to ground. When it comes to PLC inputs, terminology can be confusing, and the best thing you can do is see if the manufacturer provides a simple diagram, maybe like this or like this, that illustrates how a sensor would be connected to the particular input module. And if you see it's connected up with the sensor's power supply like this, and they're showing it coming in the module like this, that by itself doesn't tell you whether it's sinking or sourcing, because it actually could be a sourcing module and the transistor could be from here to here, and thereby sinking current to ground by this route. That could be the case. So they may have an arrow showing the direction of current. They may just say sinking. Make sure you know if they're referring to the sensor or to the input module. What's their frame of reference? And if that doesn't clarify it for you, usually most PLC manufacturers will have a simplified schematic of what's going on inside each of these inputs. And it'll show you something like this. And you can say, here's the input terminal, and it's got to have current going in this direction in order to get to ground. Therefore, this must be a sinking input, which requires a sourcing sensor to operate it, and vice versa. So just a little bit more detail on things that might be confusing. So here's a sensor again, 3 wires. It has V plus, it has ground, and then it has the output. In this case, it's a PNP type, so the internal transistor connects between the V plus and the output, and the current would go in this direction, the direction of the arrow, and leave the sensor as a sourcing sensor. And it goes through the load and then back to ground, so this is the path of the current. Now, we can simplify this and say, well, we don't care what type of transistor is in here. All we care about is that it's acting like a relay contact or a switch between V plus and the load. Sometimes you'll see sensors that are marked normally open or abbreviated with the letters NO. Sometimes you'll see normally closed, abbreviated as NC. If it doesn't say it, then you just have to assume that when the sensor is detecting whatever it is that it detects, that the output will be turned on and that current will flow through it and the load will be energized. So that's assuming that it acts like a normally open switch. And let's say this is a sensor that detects the proximity of metal. You bring some metal close to it, the sensor turns on such that the transistor starts conducting and current will flow through it and through the load, and now the load is turned on because it's sensed metal. Same thing if it's a switch here. This could be a push button, it could be a limit switch, it could be some other relay, it could be the transistor inside the sensor. when it's shown like this, that means normally open. That means some sort of an action has to be taken in order to close this contact, converting it from normally open to closed, and thereby allowing current to flow through the load. But you'll get sensors sometimes that are marked NC, meaning it's just the opposite. It's set up so that the switching element, whether it's a contact or a transistor, and it has nothing to do with whether it's NPN or PNP, it's set up so that when activity is made that affects the sensor, that this contact is turned from normally closed to open, and therefore it breaks the circuit. In other words, if the thing is not sensing what it's set up to sense, then it's on and current goes through the load. But when it does sense the thing, proximity of something, whatever, now the virtual contact opens up and the current stops flowing. That would be the NC, or normally closed, arrangement. Normally open, normally closed has nothing to do with the NPN, PNP question. It has nothing to do with whether you're operating a relay coil or a lamp or going into a PLC or DCS input module. It has nothing to do with sourcing and sinking. It's strictly telling you, does the thing pass current to the load or does it not pass current to the load when the thing that the sensor is there to sense is happening. Let's look at a typical PLC input module. This one's simplified a little bit, and it's only an 8-point module, so there's 8 inputs. These days it's more common to have inputs with 16 points on them, but some smaller PLCs still have 8 inputs per module. And this is DC, and we're presuming it's 24 volts, although I'm not specifying the voltage. Most of these modules have a fairly wide range of inputs that they'll work with. You just have to look at their specifications. So I have the power rail on the left side, which is connected to V+, the positive side of the power supply. I've got a power rail here, V-, that's the minus side of the power supply. One thing that's common with PLC input modules is commoning of groups. So in this case I have a group of 4 inputs which are internally commoned, and they'll come out with one terminal that serves all 4. And then similarly for the second group of 4. Not all input modules allow commoning the way I'm going to be showing it here. Some do, some don't. Again, you just have to look at the manufacturer's spec sheet, data sheet, or the manual for that particular module to see what you can do. In this hypothetical module, these can be sourcing or sinking depending on what you have the common for each group tied to. In this case, the common for this group is tied to V-. So it comes in here and all these 4 are tied to V-. This group of 4, its common goes to V+. I didn't show a line coming over from here, but you know, ideally this would make its way back to here one way or another. So I have a push button switch, a relay contact, a selector switch, one of several schematic symbols which can be used for that, and I've got a 3-terminal or a 3-wire PNP sensor here. So if I push this button, current is going to come from V+. Remember, current goes from plus to minus in conventional current flow situations. Goes through the push button and it flows into the input module, and it goes through that, does its job internally, probably turning on the LED of an optocoupler, and then it comes out the common and returns to V-. So this would be considered a sinking input module, because we're looking at it from the perspective of the input module. So it sinks current. It gives a place for this current to go to on its way back to V minus, so it's sinking. Here's a relay contact. It's doing the same thing. The switch. Here's our 3-wire sensor. It's going to have 2 wires for the power supply, so one of them is going to go to V plus, another one's going to go to V minus, and this will be the output of the sensor, and it's going into the PLC. The PLC is sinking current, but from the sensor's standpoint, it's sourcing current, and it should be, since it's a PNP. So current is coming from V plus, going through the internal PNP transistor, and then out of the output, and then to the input, and back to V minus. So you can see how a source goes into a sink. Now let's say if we had the same inputs, but now we've got V plus over here, so now we're pulling current out of these 4 inputs on the way to V minus. And this is quite common. A lot of times equipment you're tied into has contacts which can only go to the minus side of the power supply, therefore they must be sinking. Regardless, current will now flow from V plus through the input module's optocoupler or opto-isolator, goes through the push button when it's pushed, and returns to V minus. Same thing if a relay contact closes, same thing if the switch is closed. 3-terminal or 3-wire sensor, it still needs power regardless of whether it's sinking or sourcing, so V plus has to get to it somehow, and it goes into its positive power supply wire. The negative power supply wire or minus wire goes to V minus, and this is the output here, and because it's NPN, it's sinking, it's expecting to pull current into it and then to V minus or ground or common. These module points here are, as I said, intended to be set up as sourcing current. So the current is sourced by the input module and sunk to V minus through the NPN type sensor. Although this little talk I'm giving here is primarily about sensors and the PLC input modules or other similar equipment that they are connected to, I'm just going to do a quick look over PLC outputs and how syncing and sourcing may apply to them. I've shown this as one module, but it's just a representation of different types of modules. I'm dividing them by dashed lines, so let's look at the first section here. You could have a PLC output module that's a relay module. So it just has relay contacts inside of it, which the PLC or other logic control, whether those contacts are open or closed. Almost always they're normally open contacts, so they get closed. So when they're turned on by logic, the contacts close. Now, they may be listed as having outputs, or they may just be shown as having a relay contact with 2 terminals. It varies. You have to look at the data sheets. But in this case, I'm showing that it's not grouped with any other contacts in the module. Each one has 2 points for a wire to come in and a wire to go out, or vice versa. If this is a AC module, a relay module typically has no AC or DC designation, although occasionally you will find ones that have snubber devices to protect the relay contacts and cut down on sparking and things like that, or arcing. So again, you have to look at the data sheets, but mostly they're just isolated contacts. That's also called a dry contact, meaning it's not connected to anything else internally, nor is there any power applied to it internally. It's up to you to provide power to whatever circuit is connected with these. In this case, I have V plus shown. It's putting current from there through the relay contact, out of the relay contact, and then in this case to a indicator lamp, and then the current has to return to V minus. Or you can have one that's going the other way around. Here I have a relay coil, but again, there isn't really any input or output to this type of thing. It's just 2 terminals per contact, and you can use them any way you want. If it's a triac module, which it most likely is if you're using AC, although again, you can use AC circuits with relay contact outputs. That's quite commonly done. And many times they do have an RC snubber or some other device to minimize contact wear and tear, and for other reasons. But here I'm just showing a triac. One side of the AC is connected to here, it goes through the triac, this is the output, and then it goes to some AC powered device, and then it returns to the other side of the AC line. This isn't a sink or source situation, because with AC the current is going both directions. Now we have a transistor output module, and this is set up to be sourcing. It's going to have a common in it of some sort, most likely, although there are some that have 2 terminals per output. In this case I'm showing one that has multiple outputs common together, but I'm only showing one of them, but there's more down this way. So V plus would typically come in to the common point, go through a PNP transistor. It's a PNP because it's a sourcing module, and then current flows out of the transistor, out of the module, and goes to a relay coil or whatever device you've got that is the load, and then finally the current returns to V minus. So in this case, the positive power supply is being switched by the transistor, and it's the source of current that goes to the load. So it's a sourcing module. But you can get ones that have a PNP in them. So here's V minus, and it's going to the common of the module. So it's serving more than one transistor, and it's an NPN transistor in each case. The emitter is the common side, and then the collector is the output. We're still calling it an output even though current is going to flow into it. And it's called the output because it's the side that is not common with the other points in the module. V plus is out here, and it goes through a relay coil or whatever. You have to observe polarity if there is a polarity on the device, and it'll flow, the current will flow into the output. It'll go through the transistor and return to the common, which is then also connected to V minus. So the current is flowing from V plus through the load, through the module, and return to V minus. In this case, current is being sunk from the output to V minus. So current is flowing into the output, therefore it is a sinking type module. It's really not that complicated.